So last thing I wanted to talk about in today's lecture is prefetching, or the technique of prefetching. So what is prefetching? Well, you speculate that you're going to be using some, let's say, either instruction or data in the near future. So you can say, I think I'm going to be accessing some cache line in the near future. Now, you haven't accessed it yet. The processor hasn't gone to initiate this transaction yet. But because you have some reason to believe that it's a good idea to go do this, you speculatively go and fetch that data from either memory or a farther out level of cache and bring it into a lower or a nearer level of cache. So this is the basic idea of prefetching. Well, what does this look like? Well, there's a couple different varieties of prefetching we're going to be talking about today. So we're going to talk about hardware prefetching, which is a complete hardware-based solution where the hardware tries to detect what is a useful thing to go bring in. We're going to talk about software prefetching, where the compiler or the programmer decides what is a useful piece of data to go get early. And we can talk about mixed schemes, where it's software hinting to hardware potentially about when it's a good idea to go bring in data. OK, so important question that comes up on the slide here. What types of cache misses does prefetching affect? What does it affect? Well, we're bringing in data potentially before it's actually used. But, so that sounds good. That sounds all good. But we're actually polluting our cache potentially with data we don't know that we're going to need yet. So there can be downsides to this. So let's go through the 3 C's. Capacity. Does this affect capacity? Well, yes. It actually affects capacity was effectively a negative way. You've effectively polluted your cache because you've prefetched something into your cache, and you could potentially make the cache have a smaller effective capacity because of this. And this actually trades off. This is the sort of similar sort of thing with conflict misses. You're effectively putting data into your cache that if you have a really bad prefetcher, a prefetcher which actually goes and brings data in that is not accessed ever, we'll say, or not accessed in a short period of time afterwards, you might actually be both polluting the capacity and creating more conflicts. So you can bring it into a line, and because of this, some other piece of data that gets brought in has to go evict that now. It takes time to go evict it, or at least has to make some decision, and it might even mess up the least recently used policy or the replacement policy. OK, so why would we do this? We said this is bad for conflict misses, or increases our conflict misses. Where does prefetching help? Well, it can actually really help with compulsory misses. So misses where you just miss on effectively cold data. The data is just not in your cache. You have to go get it and bring it in. So let's say a first touch data or a compulsory miss. It would be really great if the prefetch system, or either hardware or software prefetcher, could bring that data into your cache preemptively. And by bringing that data into your cache preemptively, either reduce the latency or remove the latency completely of compulsory misses. So how do we reduce that miss cost? Well, let's say you go to take a cache miss on a line, and the prefetcher already has sort of started to go get that line from the main memory. The miss status handling register could detect that there's a miss already in flight for that line and not actually send out a subsequent request and just wait for that data to come back. And this can decrease the latency of a compulsory miss or decrease the miss cost of compulsory miss. Alternatively, the compulsory miss could just go away. If the prefetcher is really on its game, it can bring the data into your cache, and by the time you go to access that data, it is like it's clairvoyant, if you will. It already knows that the data that you were going to access in the future, and it's already pulled it in, and when you go to access it, it's already there. So prefetching can have some pretty big benefits there. But like all things, including caches in general, you need to make sure that what you bring in is used with high probability. Otherwise, you're just going to pollute your cache. One last thing I wanted to say is that we're going to see this is that instruction caches are usually easier to predict for prefetching purposes than data. Why is this? Well, instructions are very well behaved. Typically, you execute one instruction, then you execute the next instruction, then you execute the next instruction after it. And yeah, there's branches, and programs do have a fair amount of branches, but there's a decent chance you're just going to be executing straight line code, especially in something like a loop where you're going to be executing straight line code for a while, then hit one branch at the bottom and go back up to the top. So your prefetcher can many times be very effective for that. Data, on the other hand, usually data misses and data accesses are a little bit more randomized, but not always. Sometimes you're just going to be accessing, let's say, straight line data, something like a mem copy or something like taking an array and reading the whole array, and a prefetcher can be very effective there also. So let's take a look at some of the issues with prefetching. We've already touched on some of these things. In order for prefetch to be good, it has to be useful. So it should produce hits in the cache. If the prefetcher is actually producing mostly misses in the cache or bringing in stuff that either instruction, if it's on the instruction side, it never executes, or on the data side, it never tries to go do a load or a store on, it wasn't useful. Now, things get a little bit more complex here when you start to think about usefulness. You have to start thinking about timeliness of the data. So what do I mean by timeliness? Well, if you prefetch a piece of data into your cache, but you do it too early, it's very possible by the time you go read the data, it might have gotten evicted from the cache. So if you bring it in too early, the prefetcher might have just wasted bandwidth and wasted energy going to the next level cache or going out to main memory, and that data may not end up being useful because it wasn't timely. You might have gotten the address right, but gotten it there too early, or it might have figured out that it was too late. So how does this happen? So let's say you determine that this one line is really good, and you're with high probability you're going to need it. So you speculatively want to go pull it in, but the prefetcher decides this the cycle after the load happened to that line. Well, it didn't help. Maybe even the cycle before, it just wouldn't help because you're too late, effectively. And as we've already discussed, you can have significant cache and bandwidth pollution here. So you can pollute pollute the capacity of the cache, and you can waste a lot of bandwidth. And this is a problem if, for instance, you're on a multi-core chip or a many-core chip, and off-chip memory bandwidth is really important, and it's a really limited resource. You may not want to actually have any prefetch turned on because you might just be wasting bandwidth. So it's a speculative execution sort of thing. So you're going to be trying to pull in data, but it's speculative. You don't know 100% that you're going to be using that data. And any time that you bring something in that you don't use, you've effectively wasted bandwidth. So this is a big challenge here. From the bandwidth perspective, usually a good place to put a prefetcher is maybe somewhere between, let's say, a level 2 cache and a level 1 cache, especially maybe on the instruction side. But you can think about this that you want to basically pull in data, and this bandwidth here is relatively inexpensive from your level 1 to your level 2 because it's an on-chip bus, it's directly connected, you can make it relatively large. Coming out of the level 2 cache, though, usually, or going out of, let's say, the last level cache out to main memory, that's usually expensive bandwidth. So sometimes people come up with prefetchers that only prefetch, let's say, from a level 2 cache to level 1 cache, but if it's not in the level 2 cache, the prefetch just gets dropped. So that's a pretty common strategy here. OK, so let's start off by looking at the simple case here of instruction prefetching in hardware with a basic example, something like what they had in the Alpha 21064. So it's a very relatively basic processor, and we want to look at what they did for performance. Well, they actually added an extra little buffer here that they're going to call a stream buffer. And the stream buffer here is going to store the next line that is likely to be used. So if you take a cache miss, this is on the instruction side, for a particular instruction cache block, let's say block I in this example, you decide, the hardware decides with high probability block I plus 1 is probably going to be used. But instead of polluting our instruction cache in their design, what they did is the subsequent cache block is actually stored into the stream buffer. So they didn't actually pollute their cache. This is kind of like the a little bit of extra associativity here, but only for the next predicted line, if you will. OK, so in this example here, what would happen is you'd be executing out your level 1 cache. And let's say you fall through. The code just falls through. There's no branch at the end of the cache line, and you fall through. Well, the predictor actually did really well here, and it overlapped effectively the cost going out to either the level 2 cache or going out to the main memory for that subsequent cache line. So it hits in the stream buffer, and the stream buffer gets moved into the cache, and the hardware system says, or the hardware prefetching system says, aha, I went and I'm now executing block I plus 1. Maybe it'd be a good idea to go and prefetch block I plus 2. And effectively what you're doing here is you're overlapping the execution of block I with the fetch of block I plus 1. So you can be doing two things at one time. You can be using the CPU fetching, executing from block I, and you can be using the cache moving data this way into the stream buffer for block I plus 1. And likewise, when you go to fetch, when you're executing, let's say, block I plus 1, you might be fetching block I plus 2. OK, so that's the instruction prefetch side of the world. Life gets a little more complex when we start to go look at the data prefetching. Now, why is this? Well, it's not as well structured as instructions. Instructions, you just typically blast through the code, keep falling through. In the data world, you don't necessarily know because you've went and accessed, let's say, address A, that you will go access some other address because of that. But you can try. So people have implemented a bunch of different prefetchers that help to some extent. The most basic thing you can think about doing is actually just doing something very similar to as we had in the instruction example. If you go and you take a cache miss on, let's say, block B, you go also fetch block B plus 1 into your cache. And to some extent, this helps. You have to be a little bit careful here, because you might be wasting capacity and bandwidth. But in some cases, this is helpful. So if you're streaming through an array, this helps. If you're doing a mem copy, this helps. This prefetch on miss. Now note, we say prefetch on miss here, but we don't say prefetch on hit, which is a little bit different than our example in the instruction space there. So prefetch on miss, it's only when you take a cache miss that you go, let's say, fetch B plus 1. Now, there's different strategies here. Prefetch on hit, prefetch on miss. You might think about doing either of these depending on the heuristics of what your hardware comes up with. So that's prefetch on miss. Maybe you actually want to do one block look ahead. So this is much more, this is basically the same thing we were doing on the instruction side here, is if you go access, let's say, block B, and this means not necessarily a cache miss, you go and actually fetch from your next level out of cache B plus 1. OK, so a question comes up is this the same thing as just doubling your block size? Well, that's interesting. Because you effectively go fetch, whenever you touch B, you go prefetch B plus 1. This kind of looks like just making your block size bigger, because this is just doubling the block size. You'd always bring in 2 blocks. But it's only a prefetch operation. So you could think about having it, for instance, just load from your L2 into your L1 when you have this example, and not actually have to go out to your last level cache. So you could think about having different trade-offs there. Also, The downside of this is that it's not just making your block size bigger. You effectively have two sets of tags here. So that's the downside of having something like this one block look-ahead scheme. But you could think about taking this example and actually extending it to an n-block look-ahead. So if you go to access block, let's say B, or cache line B, you go fetch a couple after that. And the name of the game here is you're trying to hide memory latency, main memory latency. So what would be really great is if you go to access, let's say, block B, and you know that the hardware somehow determines with heuristics. Typically how you implement these things is little watchers that watch what accesses you're doing and then decide that it's fruitful to go and actually do a prefetch. You could say, I'm accessing block B. I should start trying to read from main memory block B+1, B+2, B+3, B+4, all the way up to, let's say, big N here. And by doing this, you can overlap the latency so that if you go try to access that next block, it'll have already been there. And you don't have to wait for the latency going out to main memory. This actually can increase performance significantly. OK, so that's the basic examples. But those don't always work well. Sometimes you might have something like an array access where you're not touching, let's say, every byte in the array. Maybe you're accessing every nth byte in the array or some offset. Well, how does this happen? Well, this is actually really common if you're trying to access an array of structures or an array of, let's say, class objects. Why is this? Well, if you have a structure, you have different fields in the structure, and they are at different offsets inside the structure. So if you have an array of them, they're packed densely. And if you are reading, let's say, some subfield of a structure, and you're reading every element of that array, you're actually going to have what's called a strided access. So you're not going to be accessing byte 1, and then byte 2, and byte 3, what's called unit stride. Instead, you're going to be having some offset as you move through the array. And if the structure is large enough, what might end up happening is you may not actually want to go and fetch the next line, the next line, the next line. Instead, you might want to fetch just the lines that contain the portion of the structure that you want to go access. So what does this look like? Well, you need something like a strided hardware prefetcher. So if you see a pattern happening, typically that's when you fire up something like a stride prefetcher. So if you go look at a modern day Intel processor, they actually have stride detectors. So there's little pieces of hardware which watch the cache access pattern or the processor access pattern and will say, aha, I see that the processor is accessing cache block B plus N, cache block B plus 2N, cache block B plus 3N. Maybe we should go prefetch cache block B plus 4N. So, but N is the stride size. So you may not be pulling in every block in series, but instead pulling out in blocks that are spaced out through memory with some spacing. But with everything, you have to be careful that this does not pollute your cache, both from a bandwidth or a capacity perspective. So let's take a look at an example here. We have the Power 5. The Power 5 has a pretty sophisticated hardware-based predictor, or hardware-based prefetching and prediction scheme. So they actually have 8 independent stride prefetchers per processor, which can each prefetch up to 12 lines ahead of the current access. Wow, so that's pretty impressive. They basically have little pieces of hardware they're seeing what is a likely thing to go access based on what the program's doing and try to bring it in early to improve performance and reduce the cache miss latency and reduce the cache miss time or rate, if you will. OK, so that's hardware prefetching. We can also think about having software-based prefetching. So the compiler can figure out, aha, or maybe the programmer who's running code can say, I know that I'm going to go around this loop many times. So instead of waiting to take a cache miss when I really, really need it, which is when I have to go do this add here, let's say of A of I and B of I. Instead, we can say, OK, I know the next time around the loop, I'm going to be accessing A of I plus 1 and B of I plus 1. So let's tell the memory system that I'm going to be accessing A of I plus 1 and B of I plus 1 and get that operation out there early. So we can effectively have the software help the hardware here by doing a completely software prefetch. And there's sort of two ways you can think about doing this. One way is that these prefetches are basically just loads that'll bring the line in early. Alternatively, some architectures have a more hybrid hardware-software approach where you'll actually have a prefetch instruction. And the prefetch instruction will tell the hardware, or hint to the hardware, that it's likely that you're going to go be using this data, but maybe you don't want to waste off-chip memory bandwidth for this. So only pull in, let's say, from the L2 to the level 1 cache, but don't go take a cache miss for this because this has some probability of not being correct and shouldn't take priority over true cache misses. And if you had just a normal load and operation for your prefetch, you wouldn't be able to detect that case. So in some of the hybrid solutions, prefetches will actually turn into special instructions. Software prefetches will actually turn into special instructions. OK, so what are the issues with software prefetching? Well, software timing actually ends up being the biggest challenge here, not predictability. This loop here is very predictable. We know we're just going to stride through array A and array B. But what we don't know is we might end up being too late or too early. So you have to get sort of the right time. You have to get the time right when you actually go to access these different things. So what we're gonna do here is we're gonna say, instead of accessing I plus 1, we are going to access maybe like I plus P here. And this is a settable parameter where you can say, this is a few cache lines into the future, we can pull it in. And we want to set that correctly so that we pull in at the right time so that we can cover the cache miss latency time out to either the next level of cache or maybe out to main memory, but not early enough that we actually pollute the cache and actually cause conflicts somewhere else. So if we set P here huge, we would be pulling in data potentially way too early. So if we set this to, let's say, bigger than the array size A and B, it's very possible that we'd actually be polluting the cache with wrong data, if you will. A few other things that come up here is how do we go about trying to estimate P? Well, this is a tricky thing. Why is this hard? Well, we don't quite know what the latency is, and we don't quite know whether A and B are going to hit or miss, or whether the hardware prefetcher is going to fight against our software prefetcher, and things get a little bit complex here. And it's really just because you don't know the memory load, the actual congestion at the memory controller. You don't know whether lines miss or don't. So you effectively have a piece of dynamic number here, which is being determined at static compile time, we'll say. And then also, you don't quite know what architecture you're going to be on. So different architectures, let's say, or different microarchitectures for the same instruction set architecture might have different cache miss latencies. So if you want to write one piece of software that works on all of them, there may not be a correct value of P. So you have to think about that. Finally, I wanted to say is that you must consider the cost of the prefetch instructions. These are not free. You have to add these 2 extra instructions here. And if your performance benefit, of having prefetch instructions does not outweigh the cost of adding 2 extra instructions, it's probably not a good trade-off. You probably shouldn't be doing something like this. So next lecture, we're going to talk a little bit more about different software prefetching issues and other ways to rearrange code in the compiler to effectively bring data in a more structured manner. But let's take a look at the efficacy of prefetching. So which of these things does this help or hurt? Well, what we're going to see is, first of all, we're going to actually potentially help the miss penalty. So when does the miss penalty help? When is the miss penalty made better? Well, if you have a cache, if you have a prefetch in flight to a piece of data that you then have a demand miss for, you effectively cut the latency for that demand miss, or the miss penalty, down to just finishing the currently in-flight prefetch. So you can take that cost and make it a little bit shorter. Miss rate. Miss rate also is better. Why is miss rate better? Well, if you had a prefetch occur and it brought it into your cache, and then you hit on that data, you just have fewer misses out of your cache. So your miss rate is better. A couple other things here. Hit time and bandwidth. Prefetching, if done poorly, might actually hurt your bandwidth. So there might be a negative here if done poorly. And hit time typically is not really affected by prefetching. OK, we'll stop here for today.